let's say, about the energy communities in Europe and from Belgium. As you see, it's our fourth step this day about this topic. And today we will, you will have the chance to meet a few very great players from Belgium that are working in the field of energy communities, that are working in the living labs, that are providing technologies, know-how, and results about energy communities. And so the program of today will have interest for you, I hope. It's part, this seminar is part of the Smart Energy Digitalizing Energy in Europe project. It's a project with different clusters in Europe, from France, Italy, and Belgium, but as well in Hungary and other countries. And we try to help each other to provide some meetings between the R&D centers, technology providers, and really the objective is to meet the match between the players. For sure, this project has started 1 year ago, and so it's quite very difficult to meet very physical matching. So we have transferred it in digital way, and we hope for the last part of the project in the end of the year that we will provide you and offer you some opportunities to really to go and discover some R&D players and SMEs from Italy and France, because we can offer you some travels and so I hope we will do that for the end of the year or early next year. So today the objective is to really to go deep in the implementation of energy communities with some concrete projects, technologies, and know-how that we have in Belgium, and to provide you some information of what's going on right now. And so we have different speakers for this morning, and we hope that we can have discussion between the different presentation. All the presentation will be recorded. The slides will be sent to the players, and don't hesitate to use the chat session to ask some question, and we can have some chat session after the after one speaker or in the end of the presentation. So it's very quick introduction, and so I'll let the floor for the first speaker. It's Quentin Gemine from Blacklight Analytics. It's a new startup for that are very the core business of the startup. He will explain, but they are very strong about the energy communities, and he will speak about the enabling the energy management system for the energy communities with a technology behavior. So Quentin, we'll let you the floor so you can share your screen.
Yes, thank you, Cédric. I will do that. So good morning, everyone, and thank you, Cédric, for the introduction. So I am indeed Quentin from Blacklight Analytics. I will speak about energy management system for energy communities. And we are indeed a startup that aims really at integrating machine learning and optimization strategies into modern solutions for the management and for the smart management of energy system, such as communities, such as distribution systems, and so on. And so managing energy communities falls really within the scope of our main activities. And so I will quickly speak here, introduce energy communities from a very conceptual point of view. And so let's assume we have really a set of members, of potential members of communities. We can have like at the top right here, a production asset that can share its energy to other members within the community, of course, residential members, industrial members, whatever kind of member of the community can have. We can also have more like prosumers entities. Here we have, for example, an industrial prosumer, that can share its surplus production to all the other community members. We can have the same for residential prosumers, of course, that can also share the energy to the community. And on top of that, we can have some specific flexibility within each grid user here. So, for example, we can have storage systems that can help to improve, for example, the self-consumption of a grid user. Self-consumption being the amount of renewable energy that is consumed locally over the total amount of energy that is produced locally. But it can also be used within a community to improve the overall self-consumption rate of the total community. And as you can see, it can quickly become a spaghetti of energy flows, and it's not naive. It can be quite complex to manage in an optimal way all these energy flows within the communities. And so what you usually want is some kind of energy management system that is dedicated to communities, of course, to organize all these energy flows and the associated financial flows, of course, to really steer the operation of your community in the good direction. And so here in this presentation, I will speak about this energy management system, what they can do, and I will also say a few words about AMEO, software solution that we develop at Blacklight Analytics that can help you organize this energy management system. And so what is really the goal of the energy management system? Well, it's to make the best out of the power profile, the energy profile of all your members, to try to organize them all together to minimize some kind of cost or some kind of objective. And so we know that within a community we have many kind of different profiles that can live together. We can have residential profiles that typically have a peak consumption in the beginning of the day and in the beginning of the evening. We also have some industrial profiles that most of the time consume their energy during the day and consume only a few amount of energy during the night. And in terms of production, we have also different kind of profile where we have solar production profile that are very typical and that peaks around, of course, 10 a.m. And also, as in the previous picture, you can have a wind turbines or any other kind of renewable asset. And for wind production, it's at best very variable production and most of the time quite chaotic. So it's also a very, very challenging profile to integrate and to optimize within the community. And you want your solution to take all these profile and to try to share a power within user within the community between user and to take intelligent decision to optimize the behavior of your community. And so optimizing the behavior can be defined in different ways. Here in the presentation, I will consider that what we want to do is really to minimize the sum of electricity cost of all the community members. So you take the energy bill of every member, you take the sum of all these bills, and you want to minimize this amount of energy. And so this amount of cost, sorry. And so here we have a formula that is the sum of cost that we want to minimize. I will briefly describe this formula. So first we have the sum over time and over all the community members of a first metric here, which is what? Which is actually the supply and grid import price. So really the price per megawatt hour to get energy from the grid times the consumption of the grid user minus the community import. So you remove from the imports from the grid, you remove the import you got from the community, and these first two terms multiplied together are what you pay for getting energy from the conventional grid. And you have another cost component, which is the community import price times the amount of energy you import from the community. So one first term about getting energy from the grid, and another one for getting energy from the community. And these two terms are fall within the cost category of what you want to optimize, of course. And the second part of the equation of the formula, you have first the community export price and the amount of energy that you export to the community, which altogether accounts, if you multiply them, for the the revenue you get for bringing energy into the community. And of course, we have the selling and grid export price. So what you get for selling energy back to the main grid times your production minus the share of production that you dedicated to the community and not to the grid. And so altogether, these terms are, of course, the revenue part of your equation. Well, we can have some tricky situation like these few days where we got like negative prices on market, but let's keep that out of the discussion for today. But most of the time you have a cost component and revenue component, and you can play within you have some flexibility to decide if you want to choose between bringing energy to the community or to the grid, and the same for the consumption. And so about the control means that you have, so about your energy management system, how it can works. Well, first it can use demand-side flexibility if it's available to basically tune the terms we just saw in the equation. It's a complex topic that should have the dedicated presentation on its own. So I will keep this topic out of the scope of this presentation for today, and we'll focus on another kind of physical control mean, which is the storage. And with storage, you can have a lot of flexibility, of course, but it's a quite complex device to operate. Why? Because your control mean, actually, your flexibility evolves over time. And so here in the small chart that we have here, we can see that we can, for example, charge or discharge a battery within its maximal discharge power and maximal charge power. But as time goes on, as you charge or discharge your battery, the state of charge will, of course, evolve, and you will have a limited action space. So at the beginning, for example, if you have around 50% state of charge, you can both charge and discharge. But as you will charge and put more energy into the battery, you will reach the maximum amount of your battery, and you will have first to reduce the amount of power you can put into the battery, and then you will reach, of course, 100% state of charge. You will not be able to use this asset anymore at that time to increase your consumption or to store renewable production. And so then, of course, you will be able to discharge your battery and to bring energy out of it. And so at the beginning, you can bring most, you can reach maximal power discharge. But again, over time, as you reach the 0% state of charge, as you are getting closer to it, you will reduce your power discharge and up to the ultimate point where you don't have any power anymore into your battery. And so it is complex. Why? Because decision that you are taking at some time will impact the kind of decision you will be able to take later on, for managing your grid. And it's a quite complex flexible asset. But we also have some virtual control means within the community. So what are they? Basically, it's how you want to allocate your local energy within your community members. And so is it virtual because it only affects the metering data? The production process and the consumption process, they are there, but you decide to match some local production that are at a specific grid for a specific grid user within the community, and to say, okay, a share of its production was exchanged or is exchanged with another user, and you virtually, for example, update the meters to consider that a part of this energy was exchanged within the community and not through the conventional grid. And so these control means they are, of course, the share of local renewable production that is allocated to every member. So within our equation from before, these are actually the A, so the A. So if you decide to allocate more energy to a community members, you decrease its consumption as seen from the conventional grid, from a metering point of view, but you increase, of course, the amount of energy it brings from the community. And there is also the share of each member's production that goes to the community and not to the conventional grid. And so it's the other decision variable here. It is that you can see, and it can again change the production as seen from the conventional grid. And so you have P minus Y here to decrease your production. And of course, there is a new term that is the one that you are sending to the community. And so about the optimization, control, the optimal control you want to apply to your system to manage it in an optimal way, you can do it in two steps. So first, you want to plan both physical and virtual control means under uncertainty, eventually in a receding horizon approach. So what does that mean? So first, you will optimize all these terms. So you are under uncertainty, and you will say, okay, I forecast that my system will go into this direction. I will optimize both my physical control actions. So I will update consumption and production variable by changing the behavior of my user. Using physical control means, but I will also consider for that I can update my virtual power exchanges to really optimize the whole formula, the value of the whole cost function here. That's the first step. And then you can, depending of the regulation, of course, but you may be able to run an ex post optimization of the virtual control means as soon as you know with certainty all the energy flows. So this, the virtual control means, so the share of energy that you bring from or you bring to the community is virtual. So you can change it afterwards for metering purposes, for example. And so you will not be able to alter your consumption and production anymore, but you will be able to play again with a few other decision variables as soon as you will know with certainty all the energy flow within your community. And so I will speak a bit about AMEO here. So AMEO is a software solution that we develop at Backlog Analytics, and which is dedicated to the advanced management of energy data and operation. And it can collect energy data from many sources, run many kind of data processing steps and operation, run forecasting and decision-making algorithm. And so managing energy community really falls within the scope of this solution because it's really about getting data that describe your community members and taking decision to optimize technical operation, economical and technical operation of your community. And so how do we organize and do we represent community within AMEO? Well, we have a community within which you have member, and so a member can be a very simple member with only some demand, you know, but you can also have a prosumer member that have both demand and production, or even more complex one that have demand, production, and a battery, a storage system, which itself has some other behavior and processes like charge, discharge, and state of charge. And you can also have many members, of course, in your community. And so as soon as you model and you account for all these members and processes within AMEO, you can perform some active community management. So really make the optimal control works, you know. And so you take all the demand and production processes, as well as the state of charge of your batteries over time. And first, you run some learning algorithm of your demand and production behavior, and you take the learned model and the actual value, last value that you know about demand and production, and you send it to a forecasting step that will forecast the evolution of those demand and production for all your members within your community. And this feeds an optimization step that use these forecasts and the information it has about current state of charge within your storage system, and that outputs decision, such as for example, physical control means like charge and discharge that are really effective at current time. And of course, some virtual control means that are for now only the expected local production shares, because you will potentially be able to change this virtual control mean later on in ex post. And so these are just the expected value that will be updated as soon as you have a better knowledge about your system in the future. And so this ex post optimization, it takes again the demand and production processes and runs an optimization step. But the difference here is that it does not require forecasting because it knows everything. You know, it runs ex post, so it looks at past data that is available. It will slightly update and re-optimize the local production share you computed, and so it will really give you the definitive local production shares that are allocated among community members using the known and the certain consumption and production data of all your members. This, of course, calls for a lot of R&D and innovation to make energy community works and to make them works well in particular. We of course have machine learning. Machine learning is one of the cornerstone, of this solution. Why? Because you need to learn and understand the behavior and how the demand and the production processes will evolve over time and in the future, in particular, to manage optimally your community. You have optimal decision making under uncertainty, and so here it's really about taking decision for an expected, forecasted state of your system, not knowing with certainty what you will gonna get, but taking decisions that are optimal, even though there are some uncertainty in your system. Of course, it can be built on top of machine learning algorithm, of course, and using applied mathematics. But there are a lot of solutions for that. But it's a quite a challenging R&D topic too. And last one that is somehow related, of course, to the two others, it's about optimal bidding. Why optimal bidding? Because optimizing self-consumption or energy exchange is not the only way, to optimize energy bills of community members. You can also, as a community, decide to interact with energy markets and to procure energy at some cost. And these costs, you want them, of course, to be as low as possible. And so there is also some challenge about bidding and participating to energy markets that gets into the overall process of taking good decisions for energy communities. And these topics, these innovation topics, they are also worth not only for energy communities, but for many other use cases, that are somehow related to energy communities. As soon as you become an active grid user, you can participate in energy communities, but you can also have some new way to consume, some new way to react to price signals, to play with markets, commodity markets, to flexibility markets, and to offer services to grid user. And so it's really a lot of R&D topics that are used and very useful for managing energy communities, but also for the energy transition in general and for a grid user becoming active, which is really a big topic right now. So that was it for my presentation. Thank you very much. I hope you enjoyed it, and I wish you a good morning with some very exciting presentation to come.
Thank you, Quentin. Nobody has yet started the chat session, but I have a question that I think it's a lot of people are wondering. Every time that we have an energy community that it's popping up in the market, we see that that it's quite complicated to put the energy management system. And it seems that every time we relaunch all the system, how do you see a way to offer an energy management system that is more open and the standardization, let's say, of this system, and not to reinvent ourselves every time because it costs quite a lot? How is your vision about that?
I think there are two challenges there. First one is one that is being solved, I would say, right now, because there's been some years we've been working on that topic. It's about understanding the behavior and what you want to do with all these microgrids, energy communities, and all these new entities, within energy system. And so we had to understand their behavior, the shared behavior and the shared goals of all these projects, and to come with data structure and with software solution that are flexible and modular enough to cover these similar and complementary use cases. I think it's something that is being solved right now. At least is what we do with AMEO in Blacklight Analytics. So that's a first answer, I would say, to the reusability and to the getting the system at scale, into operation. And the second part is about data, and for energy transition, but also for any kind of other process, that relies on some kind of automated decision making. it's about bringing data into the system. And it's also a challenge that is somehow being addressed, but not only, of course, for energy communities. It's about using smart meters, but it's a hot topic, of course, but not only smart meters, but using these 15 minutes meters that you have, for large industrial consumers. Usually the DSO, they have the data, but they may be quite complex to get now, on a consistent basis and at a high frequency. But we see that DSO are more and more working on a digital solution, numerical platform that bring this data to market players, so that ease the flow of getting energy consumption and production data of a grid user to this software solution that will be able to optimize the behavior of their users. So that's the second, I would say, topic that needs to be well addressed to make them efficient. But for both topics, I think we are in a very good direction to make this work well.
All right, so it's very important to follow the IO program energy from Elia, I suppose, because it gives some keys over the data and how we can use it as a player. And for sure, Flux50 and ourselves, we are helping the different teams this year and last year as well. So I think it's quite important, as you said. So thank you, Quentin.
Thank you.
And we will follow this morning session with the a living lab. So it's very important to we need living labs in Belgium, and for Flux50 and TWEED is for sure the most important thing. It's to prove that technologies, R&D, economy, and more the sociologic aspect as well are taken into account in this field. And so I'm very happy to give the floor to Martin Messagi from the Green Energy Park. And he will speak about the need of these living labs as a bridge between R&D and the economy. Martin?
Thank you very much for this introduction. I will try to start sharing my screen any moment now.
We see it, not at full screen, Martin. Ah, yes, perfect.
Here it is. Good morning from my side as well, everyone. I'm indeed Martin Messagi. In fact, working at the University of Brussels in a research group called AVG. I'm leading that research group with my colleague Thierry Koosmans. We are over 30 researchers, and we are indeed operating or starting to operate and starting to learn how to manage a new living lab. This is fully together with a company, a non-profit organization that has been founded in 2019, I believe, and that's called the Green Energy Park with director Jimmy Van Moer. And it's in this construction that I would like to talk today about how to accelerate with the living lab and how to start up a living lab, as that's of course not that straightforward. I think very important to start with is to acknowledge the fact that we strongly believe since some years already that a way forward in research, in R&D, is co-creation. I think this is a fundament, and I think it's even more true in something as dramatic, let's say, as an energy transition. Because this is not only about technology, this is about many different players. This is about hearts and mind of the public as well, as we have seen, for instance, recently in Flanders with some changes in legislation. So co-creation. Then another point that I would like to raise first is, of course, as as research group in energy and sustainable energy, I would like to focus on our research topic as such. As such, we work on sustainable multi-energy systems, and I think that this is important, maybe in comparison with other groups, is that we do not look to the component itself. so to speak. We are not here to optimize a single component. We have colleagues that do that. We have a battery team at university that, of course, makes the best and most efficient battery, let's say, possible. But this is not our goal. Our goal is to look to a system and to look to a multi-energy system. So to look to electricity, not only that, but also to heating, cooling, hydrogen, e-fuels, mobility. We come out of an e-mobility history, I would say, but also to water and data. So a fairly big interpretation, I would say, of what an energy vector would be. But the problem that we see is that fairly all these components, let's say they exist or early stage on market, they are fairly efficient, these components, but the problem starts when these components are combined in a larger system. And apparently we are not efficiently managing them, I would say. And I think there are a lot of gains on that level to be done in system integration of, think about the CHP, connecting that to your battery at home with your PV panel, and understanding when that electric car that you have at home wants to charge or discharge, and so forth. So a lot of gains still to be made. Our research focus on that is actually on the system level and on the interdisciplinarity of it. So we are not only engineers engineering the technology together with industrial partners, but it's also from a socio-economic point of view, it's also from a sustainability point of view, and so forth. What we directly saw is what we need, and I think is also what we saw from, we are very active in Horizon 2020, European context. And also from there, we saw that even more so for back then the draft versions, let's say, of Horizon Europe, we saw that the TRL, the technology readiness level of these projects goes up. And there is really a need, like we heard indeed in the introduction, that there is really a need to showcase and demonstrate single components. And so if we want to be relevant in the future in Europe as well, we need demonstration zones. So we need to build a demonstration living lab. And for us, on top of that, the knowledge that we would bring lies in, let's say, general terms in data-driven analytics, like we have seen in the previous presentation. It's a huge issue that can solve not only energy management questions, I believe, but many other research questions we would have. So database and monitoring platform on top of this demonstrator living lab with a lot of user experiences is really needed. So we early on 2018 understood that that is something we would like to build and really needed to sustain our further research as well, obviously. But it's not only about that. We can build a living lab, then we have all the hardware, let's say, we have all the copper in place to play with. It's not only about that, of course, and an energy transition in itself needs also a co-creation ecosystem. And that is why we are early on, 2 years ago, we, as university, we set up this company called the Green Energy Park that would help this energy transition, not only from a traditional university or research institute point of view with research and development, so classically your TRL, technology readiness level from 1 to 6, but really helping there the step 7 and 8, closing the gap towards full demonstration on market, which, as you know, is TRL 9. The point there also is that we have seen that beyond the TRL 9, there is also a great need. We can build super complex systems with a lot of data-driven new algorithms, IoT, and so forth. But then, of course, we also need first the technical skilled people that are able to install it, these components. And then secondly, if something happens, we need someone that can maintain it and restore it, I believe. So actually in an energy transition of something as complex as this, we also believe that the higher TRLs, we call it then, in education and training are very much needed. So the Research Institute as such would still do research and have state-of-art labs. Living Lab, as it's going really beyond the scope of just academic research, it's with the help, I would say, of an external company maintaining that. Then we are thinking about incubator and startups. And later on, it should also become an expertise and training center. So it's fairly a bigger ambition that we have, and to help that, we have different steps I would like to show to you that we did and that we foresee for in the future. Because building a living lab, actually the basic problem with especially the size that we are seeing is that it's quite big. We are thinking about a 20 megawatts living lab, so you can understand that the investments needed are very large, and that's not easy to convince everyone at first that we directly need to start building that, of course. So there are some intermediate steps, let's say, that we would like to take to convince investors to invest in every step, let's say, a little bit more. So step one for us, end of 2017, we have founded that new research team with 4 people called Avergy. And we acquired in 2018, I think, our first knowledge, our first projects on the matter. And step 2 there after that in 2020, the previous year was really securing the budget and starting to build an intermediate step, which we call the Smart Village Lab. It's a small size, it's a 1 megawatt installation. It's a small size of the living lab that we are after, I would say. Step 3 for this year, we have grown a lot. We have quite a big group now. We are with 30 people. So sustaining this is very important. And I think so consolidation is really the aim for this year. Turning around and working a lot together with strategic industrial partners, and creating this interdisciplinary R&D center. For that, we look to actually Horizon Europe, where the previous steps contained as well European money. Obviously, it was also a lot supported by means from regional scientific funds to start it up. And now this year, we have a lot of experience in Horizon 2020. We would like to valorize, let's say, that experience into Horizon Europe. And we see this as a large leverage with the budgets that we have running for the moment. Strategically, we will look more to thermal grids, hydrogen, autonomous vehicles, and batteries in those systems, as there is more research for us also still needed there together with our partners. Step 4 then, 22, we would like to start really scaling up and start building that, taking over that living lab, that 20 megawatt installation, come back to that later on. And then step 5, of course, it's what it is all about. Actually, that goes from 2018 onwards, but I think we should valorize it a bit more later on. It's really on how to help companies further innovate and how to valorize, how to develop IP together in co-creation, how to have startups, how to have spin-offs. And we are, of course, also as a university thinking there of launching an incubator to foster that better. So these are steps that we are taking. Well, it's very much a stepwise approach, of course. You try something, you learn, you adapt, and you take the following step, of course. Interesting to see maybe in 2018 onwards how we did that. Yes, we can see that in this slide. We started with doing 6 smaller projects called feasibility studies, together with Flux50 and Vlaio, the regional scientific fund. And this really actually gave us the confidence on investing, let's say, research and research activities one step further. And then later on, we acquired several Horizon 2020 projects like Renaissance, Interconnect. We had many pure R&D projects, icon projects, as they are called. And then we also start writing the first projects, Interreg and EFRO, which is actually more on hardware. And this was the foundation on building that first piece of equipment, let's say, that 1 megawatt lab. So during 2018, 2020, we have grown from 4 FTE to 30 FTE at the university in this research domain, in this research group. And very good is that we could have started this non-profit organization, the Green Energy Park, to foster even the collaborations more. This was really a big step for us to convince the university to take that. This makes it less riskful for a university to take these kind of steps. Then we have acquired, as university, ground 40,000 square meters in the, well, this is the ring of Brussels that you see here. On the northwest side, we, close to the camp, the health campus, we have acquired this blue piece of ground where we are going to develop the demonstrator and living lab further. It was a major step, of course. And what we are building today is the first version of the lab, and that is called the Smart Village Lab. This is the small first step. This is a 1 megawatt installation. It contains 4 different batteries of different technologies, containerized solutions. It contains three houses that are fully equipped with, we call it the smart home lab. They are fully equipped with the newest technologies that you would use at home to heat and electrify parts of your household. It has, this village has a parking lot in the middle of its village. It's for bi-directional and smart charging things that we would like to test. Everything is on top of every building. There are solar panels. There is a new power distribution grid to be installed. And there is a control center where we can showcase new versions of, for instance, EMSs, peer-to-peer constructions, or energy coins that are steering this little prosumer market. This is an open experimental lab that can be rented by others, with other partners in research projects. So really the aim is that you rent here, let's say, a square meter to park a car that you would like to connect to battery 3 for a very specific test. And then we would schedule this in a calendar and see when we can conduct that test. So this is a first setup to showcase that we are able to make such a small living lab, that we are able to steer the components. The step beyond this, as I said, this is 1 megawatt. The step beyond this is the full site that we see here. This is really the living lab that we intend to build. This is a 20 megawatt installation with today 21 buildings connected, with 70 different companies requesting energy. And actually the aim is that there will be an local energy community here, prosumer market, so that these companies can interchange energy. First of all, that's electricity, because there is already copper, of course, installed here. So that's easy. But of course, in the future, we also see this as exchanging on a prosumer market heat and cooling between different buildings. Of course, to build this, there are a lot of funds extra needed. So that's why the previous step was, of course, very important to really prove that we are able to do this. Actually, the orange, the small orange that you see here, this is the Smart Village Lab on the ground, the blue ground that we have acquired here as university. Then later on, what we are really after in this living lab, of course, is to try to understand the user experience, to try to understand, of course, all the data that is generated by these users, and trying to understand if we can learn something from that and how to help industry with it. So in that living lab, obviously, there will be a lot of IoT sensors. We are already installing some of them today. It's all about data gathering and large big data bases, of course. And as an R&D center in which we can help is this data-driven knowledge and how we collaborate today already, and hopefully in the future, of course, more. It's about setting up, for instance, ecosystem platforms, digital twins, and other kind of services. And this is my end slide. If you have further questions, of course, you can put them now directly in the chat or ask them directly. If more digestion time is needed, let's say, you can always, of course, drop us a mail. Also, if you're interested in European Horizon Europe calls, you would like to brainstorm on that, be my guest, of course, to send us also an email. It's really the time of the year, let's say, that we are starting to address those projects as well. Thank you.
Thank you, Martin. Very interesting, because you are providing so much technologies in one living lab. Very impressive project. I have one question, maybe for the players that are in the room, but as well for the others. If you have one technology, let's say you are a battery integrator, you have an energy management system or BMS that is linked. You have a business model, let's say, that is providing some good case in your region. How can we test it in Green Energy Park? Is it open for testing new technologies? Because it seems that it's very open-minded, let's say, living lab. So how can we, as a provider or an integrator or another player, how can we work with you in that field?
Yes. Thank you. Very good question. That's actually indeed the aim, is to be really open and to see how we can help, and that can be in many different ways. To start, how we see it is that we have, let's say, three different versions of lab equipment that we foresee. Is first of all is we have a digital twin made of the living lab, the research park that is there, so the local energy community. It's running today already. It's connected to actually a very large maquette, 6 meters by 2 meters, where we can actually see the full local energy community. But underneath the hood, there is a lot of simulation running, and we see this as a hardware in the loop digital twin. So today we are connecting bits and pieces to it. This is not for testing power over an equipment. This is only to test communication. If we can, so step one, I would say, is prove that you can communicate to others. And so that's why we have provided this piece of equipment. I don't have this in the slides here. But this is a hardware in the loop simulator, I would say, to call it like that. Partners are hooking up to that. As soon as you have proven that you can communicate well, I would say, then we can go and take a step outside. And that's should be safe at first. So that's why we have the what we call the Smart Village Lab. Actually, this is not a living lab. No one is living in those houses. What it really is, it's a lab like we know it. It's an experimental lab that is very safe. So if you have a new component, you can communicate. Okay, we can install it outside. If things fail, it's separated from the full grid. It can, the breakers will open and so forth. It's safe, not explosion safe, I would say, but still, things can happen. So it's an experimental environment. As soon as we have proven from that level that it's a power hardware in the loop, we could say. As soon as we have proven that we can put power over this component and still everything works, then I think we can have the confidence of putting it in a living lab, because it's a living condition. Obviously, all these companies will not be happy if, because of your component, let's say, they tomorrow don't have electricity at a certain moment anymore, of course. So this is today already what we provide as ID in how to collaborate on different levels of readiness level, I would say.
All right, thank you. Because I really invite all the other players to use this infrastructure, because it's so complicated to put in place, and so very. I want to congratulate your team, because it's very a huge step that you have done, and so we have to use it for new technology. Thank you, Martin.
Thank you very much.
So we follow our journey with the more a building view. Right now, it's building to grid services, and it's based on monitoring system and models. And we have the chance to have the R&D Center Cenero and Charlotte Marguerite that will present this this presentation more related to the building.
Hello. Can you hear me well?
Yes.
And do you see my screen?
Yes, but not in full page.
It should come. Now?
Yes, perfect.
Okay. So good morning, everyone. My name is Charlotte Marguerite, and I'm working in an applied research center, SENAERO. So as Cedric said, we will talk today about different projects from building to grid. So the outline of the presentation is the following. I will briefly introduce SENAERO, then talk a bit about the opportunities of the construction 4.0. Then I will present the Wallis Cities big project, in which we have several demonstrators, and I will give an overview of the innovative data-driven and model-based digital twin demonstrators that we have from building level to city level. And I will focus on one specific project in the end of the presentation, with the development of building energy management system. So a few words to present SENAERO. We are originally working in the aeronautics field, but now applying the different methods and expertise acquired in the building field. So we have different topics like advanced products and processes, smart buildings, factories 4.0, and new built environments. We are working with different partners, and so basically we are working on the flows outside the buildings and between the buildings for example, fluid dynamics simulations, and also we are looking at the energy flows inside the buildings. So to enter a bit more into the presentation, a few words about the opportunities that we have today. Today, data is, as you know, data is everywhere. Data is the key for the different technologies. And it is estimated that more than 2.6 billion objects were already connected in 2017. So today it should be much more. And among all these billions of connected objects, 40% are connected to buildings. So it's a huge opportunity we have, and we have to take into account that all this data, so we talk about different categories, traditional data, for example, cadastre, bills, statistics, but also energy performance contracts, crowd data coming from GPS, mobile phones, and sensors, weather data. So all this data can be processed through different tools and methods and create valuable results. They can be combined with different artificial intelligence techniques, for example, and tools to create web platforms, web app. So this interoperability between data and tools have to be managed in a good way, so it can give interesting results. So this availability of data can be combined, as I say, with designs and operation tools, smart technologies like blockchain technologies, IoT optimization methods. And we can, for example, think about building energy model that can be fed with real-time data to create digital twins. This can really help in the operation in a very efficient way of buildings, and combined with energy technologies and, for example, as we talked before, energy management systems. This opens up possibilities for more smart buildings and energy communities, which are connected, efficient, which can use multi-energy sources and gives good advantages like, of course, to help in reaching the energy goals for the future, but also at let's say short time, interesting prices for the consumers, for example. So all this with the combination of data and tools, we can have almost endless combination of energy sources and buildings in community level. So this has to be managed in an efficient way. In Wallonia, we are implied in Seneiro in this big project, which is Wally Cities project. In this project, the objective is to develop an innovative citizens-oriented solutions in different topics in mobility, energy, environment, governance, etc. This project is based on data and in innovative solutions to create innovative ecosystems to help in developing new technological breakthrough, to help in societal challenges and foster startups in Walloon companies. So within the Wally Cities projects, we have different demonstrators. On this slide, I just put a few of them because we have much more demonstrators, and I will focus for the rest of the presentation. I will give an overview on these projects, on these demonstrators that are here. They are on different parts of Belgium, and they are at different levels, from buildings to energy community and to city level. There are a lot of data are involved, so it's data-driven and energy model-based methods that will be developed for operation control strategies, but also to propose improvement scenarios for the different energy systems. So now I will go into the different projects. The first one I want to present is the smart ACC with a study case in WAV. So in this demonstration, we want to grab in real time the challenges and advantages of an energy community compared to traditional energy production and distribution structure. So for example, on the left side of the slide, we can see an illustration of an unidirectional energy flows structure starting from a general centralized energy source. So this is for the case of an electricity grid. We can see that it all goes in the same direction from the production to the consumers through different voltage grids. And this implies a low flexibility of the demand and production. And compared to that, now we want to move to an energy community structure with the diversity of energy sources and consumers. So we can have like traditional houses, we can have commercial centers, schools, or hospitals, for example, with different types of energy needs. We can have producers, we can have consumers, and this involves bi-directional energy flows and, of course, high flexibility of demand and production. Within the energy communities, we can have, in this case, we will have a lot of IoT data coming from different sources. And this data will be used in an energy management system to help in managing the operation of such a complex community. In the Smart ACC project, so the demonstration is located in Wavre and composed with different type of consumers. So we will have residential buildings, tertiary buildings, and for example, also commercial zones. And the objective will be the development of a methodology for optimizing self-consumption in this local energy community based on hardware and software solutions. So in the hardware, we can use the existing IoT and electricity data set and develop energy models and optimization algorithms for predictive control. The project will allow to develop a platform for different types of users, like electricity providers, network operators, and consumers. And the objective of the platform will be to develop, to plan and develop active management consumptions and management of dynamic tariffs within this virtual microgrid. In the project, the optimization of energy exchanges between the participants is the key element of the project. We will first identify and monitor the energy loads that can be shifted and create the models of these energy loads. And then optimization strategies will be tested considering different types of constraints, like physical grid constraints, but also the electricity tariff constraints and the comfort constraints. And the different types of storages will be tested to optimize self-consumption within this network. That's the first project. In the second project, which is called H2 Cube Storage, there is the study case in Mortsel in Flanders. So the objective is the development of a set of tools for design and operation of a multi-energy community. So we consider here electricity and heat with hybrid storages like hydrogen storage and electrochemical storage. We want to develop the two tools. So the first tool will be a sizing tool for local consumption, production, and storage of multiple energy sources. And this will be based on techno-economical optimization. And the second tool that will be developed is the microgrid energy management system. So this one will be based on optimization control strategy. These tools will allow the design and management of the energy community, considering the challenges of daily and seasonal fluctuations of the demand and production. The study site can be seen here. It is composed of different areas and different buildings. So the first one highlighted here is the small energy community, and with the already installed equipment, such as this solar 13 kilowatt power solar PV. There is also an electrochemical battery and electric charging station for electrical cars. And the opportunity of this project will be to install more PV to contribute to the energy community. Then we have a second important building for this community is the school, on which we can also install more PV and it can be connected to a fuel cell on another building. The district heating grid already existing will be also integrated into this community. And there is this industrial site of AGFA where we will set up a reversible fuel cell. And this fuel cell will contribute with heat to the district heating network and also help in balancing the electricity grid. Yeah, so that's the different buildings that will be connected in this energy communities, and you can see also in the white line there is the area supplied by the district heating network. The fuel cell that will be used, I explained in this slide the principle. It's a fuel cell and the power connected to a power box, and the power box is developed by the Solenco company. So on this slide we see the principle of the functioning of this fuel cell and power box. So there, on the buildings there is photovoltaics installed, and the photovoltaics gives the power needed for immediate consumption when there is needs for electricity, and it is connected to a sort of cogeneration power box, and the power box can provide heat for space heating and domestic hot water to the building, and also electricity for the needs. When there is production, when there is a production of electricity because of the PV, but no need, then the exceed energy can go into the hydrogen storage, and this storage can supply back the power box when there is a need of energy but no production, because it's, for example, because it's the night. And with this combination of photovoltaics, power box, and hydrogen storage, the building is completely grid independent and gas independent, yeah, for all the time. That's for the H2 Cube storage project. Then we have also another demonstrator, which is at the city scale. The use case is in Charleroi. The objective of this project is to develop from one side a big mixed database with data coming from IoT and audit and statistical data, data from simulations, and coming from results of artificial intelligence algorithms. In case of missing data, we will focus on public buildings and schools of the city. So once we have the big database, we can build up, develop an ICT platform that will be used for energy awareness of the citizens. And this energy platform will also be used for decision making. So for the public authorities, because we will propose the different monitoring of the building and data analysis of the energy consumption, but also scenarios for retrofitting of public buildings and scenarios for district heating extension. Because there is already, as you can see on the picture below, there is already a district heating that is being built at the moment. But as it is in the very city center, it can be extended to other buildings, but it is important to evaluate to which building it is interesting to extend it to not overload the network, or to keep this network interesting from a financial point of view. And now the last project I want to present is the TP project. It's with different let's say different buildings from the Thomas Epiron group. And the first building we studied is located in Nivelles. For this project, we use building data for different things, so to improve the knowledge of buildings, of this type of buildings, and be able to improve the future buildings in terms of energy, health, and comfort. And this building will be IoT sensors and smart meters are installed, and the data will be used for visualization of energy consumptions and used for energy billing, but also to build predictive maintenance algorithms and create alerts. So the different objective will be reached by the development of an energy management system for facility management in multi-story buildings equipped with common energy systems, as it is the case for here for space heating, domestic hot water, but in the future buildings also when it exists a cooling system. In this first study case, we have a building, multi-residential building with 40 apartments and 1 triplex. All the apartments are equipped or supplied by gas boilers for space heating, and there is 1 thermal storage for to provide heat for the domestic hot water. The building is monitored with smart meters for cold water, hot water, domestic hot water, and electricity heating also. As you can see on the graphs below, we are for each apartment we are able to follow in real time the energy consumption, and there are also sensors in the apartments to measure the ambient temperature and the ventilation rate. And the sensors are also in technical installations to measure temperatures at the input and output of the boiler, of the common boiler, and at the entrance of the different blocks of apartments, and also to measure the temperatures at the entrance and outlet of the domestic hot water storages. All these measurements allow real-time monitoring for fault detection. So we are able, as I said, to follow the evolution in time of the different temperatures. And with that, we are at the moment developing algorithms based on machine learning algorithms to understand and to be trained on sets of data that are available now, and so that they can detect and recognize faulty inputs in the future. In the project, we have different steps and different, let's say, deliverables for this project. That I try to put the general methodology on this diagram. So we started from the very beginning by creating the 3D model and energy model of the building, the multi-residential building with Open Studio and Energy Plus, to have a model that is able to recreate the energy behavior of the building. And at the same time, we used monitored data and weather data that are stored in a database. We use this data together with the energy model through calibration to calibrate this model. So it means we want to be sure that the model really represents well the behavior of the real building. So we use data to calibrate it together with optimization, but we used also some, let's say, clustering methods to check that the different apartments behave well compared to the real data. And once we have this calibrated model, we can use it into fault detection and diagnosis algorithm. So in these algorithms, we have 2 parts. The first part is the fault detection. So based on the different sensors and data we have, we can, as I said, we can detect, or let's say implement, understand what is a general pattern for normal behavior of the different systems, and be able to detect when we have a faulty input. So this is the first part of fault detection. Then we have, this is data-driven fault detection. Then we have the model-based diagnosis of the fault. So based on the model that we calibrated, we can try to understand from where the wrong behavior comes, and then send alerts on the platform. The platform that we developed for this project will be able to show the different alerts, and also it is already functional for data analysis, data visualization, and automated billing for the facility manager, so he can already now at the moment check if the different apartments, what is the consumption of the apartments, and generate a PDF report for billing for private consumption, but also for common load repartition for the different common consumption in the building. So that's basically the project that started and is going quite well, and this will be completed by the end of the year. So that was my last slide. Thank you for your attention. And I guess if you have questions, we can discuss now or a bit later.
Thank you, Charlotte. I have one question maybe for you.
Mm-hmm.
We see that you have a platform and a useful tool right now that you have built for several years. How can we use it for next projects? What are the next steps? Are you seeking for partners in different sectors or projects that you want to make involve and make improvement in your tool? Maybe you can precise that, because some players in the room are providing some projects and pilots. How can we use the platform and maybe go one step further?
Okay, so this platform is developed at the moment for one building, but it will be, let's say, it will be integrated. Other buildings can be integrated in this platform, and we can customize it. So we have the general structure that is quite generic, and the input, of course, the platform will be used for different types of inputs. And depending on the building, we can adapt a little bit the platform, and this can be reused for data visualization or alerts or PDF report generations for the customers. So we are developing a platform. We have at the moment some building cases, but of course we can, and we would like to test it and to improve it with more study cases at community level would be also very interesting. For the project with Charleroi, we will try to see how to reuse the developments for this ICT platform already developed and put it at a bigger scale of a district and city center level. So we are interested into finding new building cases or new energy community cases to improve the platform that is already generic and can be customized. Yeah.
Thank you very much for your presentation. So just for information, one presentation couldn't be presented today. It's the Grégoire Wallenborn. It's unfortunately ill this morning, so he's tried, but he won't come for the presentation. It's I think he has lost his voice or something. But it's so we have still two presentations, so we will end a bit earlier. So right now we will make a virtual tour, discover the Tor Park, and the link with Tor Park and the energy communities activities with Annelise Delnos from Vito and Energyville. Annelise.
Yes, thank you for the introduction and also the opportunity to present in this webinar. I am Annelise Delnos, and I'm a project manager of Energyville within the teams of energy markets. And I want to take you along in these couple of minutes and show you the activities of Energyville, the Tor Park, and all in the context of energy communities. Before I start, maybe one or two words about Energyville. Energyville is a collaboration between the Belgian research partners KU Leuven, Vito, IMEC, and Hasselt University, and this all in the fields of sustainable energy and intelligent energy systems. And we, as Energyville, we develop technology and knowledge in order to support both public or private partners in this transition to an energy efficient and decarbonized environment. Our activities are oriented around 6 domains which are depicted on this slide. And this makes it that Energyville has a broad research scope to provide all the necessary inputs to support this sustainable energy system. If we then zoom out, then you can see here the Tor Park, and this houses Energyville, but as you can see here, also other buildings. And Tor Park is in fact a campus which contains both businesses as educational buildings, science, technologies, and all on the field of moving towards this smart and sustainable energy transition. In the Tor Park, in the campus, we have a different variety of lab facilities, specialized equipment, expertise, knowledge, networking possibilities, and this all according to the so-called quadruple helix principle, which means that we bring together industries, governments, academics, and this all within a societal environment. More importantly, last year, Tor Park was given the label of regulatory sandbox, and this was in fact the first in its kind in Flanders. And it's within this test setup that we are able to test innovative concepts like this aspect of energy communities. It gives us a bit more degree of freedom to operate in this context. For the energy buildings, we have developed a nice tool to guide you through our laboratories, to our research activities. And the 360 degrees Energyville application gives you, in fact, a virtual visit to our buildings. And it's more or less a kind of Google Street View interpretation of the Energyville building. I will give you a short demonstration of how this works. So normally, if you open then the link, you can access our buildings. You can guide to both of the Energyville buildings, and this shows you, you can move along to the different lab facilities, but also open the tab and see which kind of labs are available within the Energyville building. Moving towards the battery lab, for example, as you can see here, we have different test equipments here to provide life cycle testing, calendar life testing, tests on temperature. We also have a lab to test the reliability of solar panels in different conditions. As you can see here, we even have an outdoor PV lab where we have multiple technologies, multiple PV technologies available. As there are various labs available, I would suggest you check them out, check the website, and also explanation of our lab, which guides you a bit through our building. Then moving along to our schematic visualization of the Tor Park, you can see here an overview of electrical assets. And there is, as you can see here, a wide distribution of solar energy, EV charging equipment. But next to that, in the Smart Tor project, we developed an appropriate IT architecture. And this facilitates the connectivity of all these assets. And in the past, we bought servers in function of a project. So these projects, in fact, operated independently of each other. In the Smart Tor project, the possibilities of cloud platforms were investigated. And this was developed and implemented in a Microsoft Azure environment. The cloud platform of Smart Tor gathers all the data flows, which includes public data, such as weather forecasts, market data, etc. But it also gathers all those local data systems. So like, for example, the data coming from our PV installations, the charging stations, but it also interfaces with other systems which we have on campus, which are, for example, prevac control systems for HVACs of the buildings. As stated earlier, the Tor Park is recently acknowledged as a regulatory sandbox. And the idea and the vision, and still the idea is that we are a key enabler of experiments with an innovative background. So we want to enable all these innovative ideas in an energy context. And the regulatory sandbox of TWEED provides all those stakeholders with the possibility to test all those innovative concepts and technologies, not just experiment with them, but also in a controlled environment. And it makes it possible to identify which kind of innovative ideas pop up and which technologies are relevant from a societal point of view, but it also guides to make profound decisions on a policy level, on an innovative legislative level. And in the end, the purpose of this regulatory sandbox is that all these experiments and all these lessons learned feed back into the market in this policy environment, and we can support any position taking in relation to all the different aspects which are linked to a sustainable energy transition. And if we then move towards the different topics the regulatory sandbox contain, we have the aspect of energy communities, which is an important one, but also thermal networks and DC networks. And if we then move along to the first aspect, which is the aspect of energy communities, where we look into this new market design, these new organizational models, we can see that in the recent years, the 5Ds, as we call them, have really left their mark on the energy transition. But if we then see at the other side of the medal, we see that this paradigm shift of decentralization, of decarbonization also poses some challenges, which are manifested already now, but also expected in the near future. In particular, if we look at the electricity provision, it all boils down to efficiently maintaining the energy balance, but all within safeguarding grid capacity, safeguarding that the grid is operated in a safe grid manner. And from the perspective of the grid, for example, the electrification of heat and transport can really pose some challenges to DSOs if a fit and forget strategy is implemented. So we mean people come home, plug in their electric vehicle and forget about it. There is no smart control. Our simulations show where we can really model the current network flows that specific constraints and issues can be expected at EV penetration degrees of 50%. So moving along this energy transition, it is anticipated that our grids will undergo some kind of challenges in the aspect of grid constraints. On the debalancing side, we have seen that these markets have shown to be really prone to uncertainty. And last year, the Belgian imbalance market hit a real all-time high when the imbalance price rose to even more than €2,000 per megawatt hour. It was in fact a perfect cocktail of having low temperatures, fog and absence of wind, which was forecasted in the Belgian zone. And this led into a grave shortage of power, in fact. And to indicate that this example is not a one-time occurrence, beginning of this year, several outages induced another spike in imbalance prices. This led to prices over €1,000 per megawatt hour. And although there was some renewable infeed, it was not enough to cool down this market. And 50 minutes later, we even went to a minus €60.7 per megawatt hour. So we went from a minus 700 megawatts of shortage in power to an overbalance of 700 megawatts, all in 1 hour. And these kind of examples really show and indicate that flexibility and also flexibility from energy communities in the end will really be the key, and we should investigate to what extent these energy communities can provide an answer to these posed challenges, or maybe if they worsen the challenges indicated here. If we consider the concept of energy communities, collective activities in general, there is a certain diversity in concept. So the definition of what is an energy community, what is a collective activity, it's rather diverse. So a lot of concepts popped up like microgrids, citizen energy communities, renewable energy communities, active citizens. So there is a lot of variety, virtual power plants, for example. And also, besides these acknowledged European concepts, also alternative forms of collective activities exist in practice as well. And this makes it really difficult to pinpoint what is the actual value creation of collective activities. And at an Energyville level, we tackled this aspect of defining collective activities from 3 corner questions. So the who, the how, and the why question. So why should we look into collective activities? Why should we generate collective activities? What's the added value? The who question, so who should be involved? Which assets should be involved, and how, of course, how do we stimulate for the formulation of energy communities from all the aspects involved. And for the purpose of this presentation, I would like to focus on the why question. So why should we formulate what's the added value of collective activities? And in order to pinpoint this added value question and to also initiate appropriate facilitating actions and support position takings in context of energy communities, a quantitative assessment is inevitable. And for this purpose, we have developed an energy system model. And this model is really able to calculate from different perspectives what is the impact of considering energy flows collectively. For example, you can see here an apartment building in which we combine all the energy flows, and then we assess the impact from a grid user point of view, a grid operator point of view, and a societal point of view. And then if we then, for example, move ahead with this quantitative method, we applied it to different use cases. And you can see here, for example, for this presentation, I focus on the aspect of energy poverty. And if we calculate all the energy flows collectively, you can see here that the grid user impact from an energy poverty point of view, he can really reduce his energy bill with as much as 30%. If we then look into the grid operator impact, as from the aspect of constraints management, you can see that providing flexibility to this market is really depending on if your collective activity is considered locally. So only the assets which are at a local level could provide all these services to your grid operator. It does not make sense, for example, to formulate your energy community widespread across the country if your constraints are only on a local feeder level. So you really have to be located at that level where your grid operator is seeing this impact from a constraint point of view. What's also important is this aspect of flexibility. We always state that when you formulate an energy community, you either look for complementarity, so making sure that you combine production and consumption in the right manner, or you will be looking for flexibility. And those two purposes can really drive or increase your added value as an energy community. If we then look at the energy balancing perspective, we can conclude that this market is in fact already open, or is really in the process of opening up for all distribution grid connected flexibility sources, regardless if you're forming an energy community or not. We know that, for example, aggregators are already popping up in this market at low voltage levels, providing the flexibility to other market participants. So being an energy community is not really a prerequisite for actually participating in this market. What is important, however, is that we guarantee that all the conditions are in place to make sure that energy communities are engaged with the grid. In this context, we must assure that this triangle of signals, so in this triangle of signals, we refer to the grid tariff, your commodity price, and even your flexibility signal, are providing enough incentives for your energy communities turn out to be grid and energy system friendly. And in order to test this interplay between the grid, the commodity, and a flexibility request, We played a bit with different grid tariff designs. As you can see here, an example of two which pinpoint how they can impact really the market. For these figures here, in fact, you can see here that depending on if you set, for example, a fixed capacity threshold or a threshold set by an economic trade-off, can influence your flexibility. For example, here, if your grid tariff is focused on a fixed capacity, which means if you trespass a certain capacity boundary, you pay a higher tariff. This has a positive influence on the availability of flexibility in the market. You see an increase from the blue reference tariff to the brownish new fixed capacity threshold with an increasing volume of flexibility provided to the market. On the other side, if we consider a grid tariff with an economic threshold, this means my actually consumed capacity indicates how much I have to pay for the grid. And this economic trade-off, you can see it seizes a lot of flexibility on the market. So in this case, less flexibility than the reference case is available to the market. So an appropriate design of grid tariffs for energy communities, but also grid users in general, is really essential. If we then move to the second part, which is this thermal network at Energyville at Thorpe Park, we see that heat and cold in general are important energy carriers in the transition. And that's also acknowledged by Energyville. And that's why also at Energyville, we have developed this 5th generation thermal network on the Thorpe Park. And this thermal network, which is called the collector, aims to provide an answer to those challenges. So the existing buildings being the Thorpe Park, Thorpe Central building, the incubator, Energyville 1 and 2, they will be coupled on this thermal network. And the buildings yet to be established, which are a couple of 8 lots in total, they will also be connected to this network on the longer run. In fact, if we consider collector, the intention is to heat and cool our buildings sustainably with geothermal energy and to exchange the residual heat and cold with each other to the max. The concept is developed to be extremely modular, and this allows also the system to grow and develop as new buildings will be implemented on the Thorpe Park. In contrast to the thermal networks, which are now rolled out today in Flanders and usually also in the rest of Europe, we allow this modular approach and makes it more adaptable and with a future-proof vision. What's also there is one of the most important aspects and innovation in this concept is that we developed as well an intelligent control system. And it's thanks to this system that these geothermal resources will be used more efficiently. And we will also be having additional services and flexibility, for example, available to also be used in the electricity grid. And this makes it a smart control, a modular approach, which is future-proof integration, implementation of a heat network at the Thorpe site. And then finally, we end up with our future vision. So where do we see ourselves in the near future? By 2023, we really want to have this fully operational living lab on renewable energy integration, and this in an urban environment. And this should be backed by engagement of an industrial ecosystem. If we look into the innovation cycles, living labs can really cover a broad spectrum between fundamental research and the market. And for us, this strategic living lab focuses on this space between applied research to demonstration and piloting until, in fact, this service and product development is performed. And we see this living lab of Thorpe Park to really bridge this pre-commercial gap. And how do we see this implemented at Thorpe Park? Well, this slide visualizes the features and the characteristics and the specific activities we want to enable in our living lab. And on the feature side, for example, we want to provide this ecosystem for stakeholders from industrial side to policy level to education and academies. We want to provide strategic state-of-the-art infrastructures. We want to have a close link to our interconnected high-quality research labs. And also continuity should be ensured to distinguish our strategic living lab from temporary pilots. And on the activity side, we really want to develop this co-development. So co-development with industry to really support testing and optimization, support innovation, and to allow for demonstration and validation of new concepts in a real life setup. And I think what's most importantly is the fact that we got this acknowledgement as regulatory sandbox, which gives us more degrees of freedom to implement these kind of innovations and to check, regardless of legislation, how is the performance of innovations, technologies, and what's the best practice from a societal point of view in general to move forward in this context of energy transition. And with that, I want to end the presentation and see if there are still open questions to be asked. Thank you for the attention.
Thank you. I think it's very clear today the chat or all the people that don't have take the coffee this morning. It's quite complicated, but still, thank you. It's very interesting. This virtual tour. It's always a pleasure to see what you can provide, and Energieville is so. Let's be honest, so strong, and with a very global view. It's very interesting. We are partners of the Energy Encounters webinar session, and so I invite the people that want to know about the Belgian view of the energy transition. We will have the global seminar on the 31 of March. And so it's Energieville that has organized everything, and so we are partner with Flux50 and Fluxys and others, Elia, I think, and so the next discussion will be interesting, and for sure we want to create the more links, more and more between the regions in this field. So thank you, Annelies, for this very interesting presentation, and so we will end with the last discussion of today. It's about artificial intelligence for energy communities, with Matthias Strobe from IMEC UGent, and so the utilization of this artificial intelligence for modeling and controlling flexible power consumption. Matthias?
Yes, I'm here. Can you see my screen?
Perfectly.
Okay. Yeah, thank you for the introduction. So I work for IMEC, and I'll start with a bit information about IMEC. IMEC is you can see my second screen now with the map of Flanders.
Yes.
Yeah. Okay. So IMEC is a large research institute in Flanders, as you can see, distributed all over Flanders, with headquarters in Leuven, where let's say the original research is located more on hardware, on chip design. But there is also research going on at the different Flemish universities, more on software, communication, and also AI. And as already mentioned by Annelies, there are also research activities well, in fact, all research activities of IMEC on energy are located or affiliated with Energieville. So there are also a number of labs at Torpark from IMEC. But myself, I'm located in Ghent. We have there a research group that works on aspects of AI, IoT, cloud and applications. And we have a research team that works there on applying AI techniques to energy data. I will give you a few examples of the research that we do, and make the link, of course, also to energy communities. So We mainly investigate consumption patterns of flexible appliances, trying to find flexibility and then use that flexibility for demand response applications. So on this slide, you can see some analysis we did on data coming from charging sessions for electric vehicles. And the main data set we analyzed is the one at the left from ELAD. There's a lot of data that we received from the Netherlands from public charging infrastructure. And the first research question that we had was trying to get an idea of typical charging behaviors. So we clustered that data based on the arrival times and the departure times of these EVs. And we found three typical clusters for the charging of the EVs. The orange cluster, where our charging sessions where cars arrive typically in the evening and are connected during the whole night to the infrastructure and are leaving again in the morning. So typically night charging when people are at home. The yellow cluster is the inverse. Their cars are connected in the morning and leave in the evening, so during work hours of the people. And then the blue cluster, the last one, that are charging sessions which are typically shorter than the other two clusters. So charging sessions where the connection time of the car is typically not much longer than the time needed to actually charge a car. So it seems like people are driving towards a charging station, but with the real purpose to charge their car, maybe do something in between. But when the charging is finished, they leave again. Did some further analysis on that, looking at especially on how much flexibility would be available in those charging sessions, which can be seen at the table at the bottom. And obviously, as could be expected, the nighttime charging is the most flexible cluster because the cars are connected very long to the charging infrastructure. Also, the charge near work during working hours has quite a lot of flexibility during the day. And then the blue cluster, where people just charge their car and do something in between, has the least flexibility and is less interesting to be used for demand response applications. Next step was then investigating how can we use that flexibility for this kind of demand response. How can we shift the charging, take into account the energy needs, the time the users want to leave again, and how can we then use that flexibility to solve some objectives which could be relevant in the broader energy system, but also for local energy communities. Like, for example, trying to flatten the loads and to flatten the peaks in your community so that you don't have to import large peaks from, let's say, the public grid, for example, which could mean a large cost for your community, or try to balance local energy production with local energy consumption so that you can become more independent from the public grid, or to avoid other technical issues in the grid, like voltage violations, congestion, etc. So we then first investigated with the flexibility that we found in those charging profiles. If we know everything perfectly, if we know perfectly when the cars will arrive, leave again, how much energy do they need, to what extent can we reach these kind of objectives? And for example, the middle graph shows you that the typical peaks that you have in the morning and especially in the evening when cars arrive at charging stations and start charging immediately, that if you use the available flexibility, that you can really create a very flat profile. The green line here, it's almost completely flat. So in theory, if you know everything on beforehand, you can really reach this load flattening objective. We did a second analysis more on trying to matching with a local production profile, which is more variable, which is this purple line on the top graph. And then we saw that we could also follow this pattern quite nicely, which is this orange line, not as good as with, let's say, the flattening of the profile, but still we could follow the general trends of the production profile. So also there, flexibility could be very useful. Of course, in reality, you don't know exactly when the cars will arrive and leave again, how much energy they will need, how much flexibility the users have, etc. So you need to design algorithms that can take this uncertainty into account and that can come up with a charging policy that is as good as possible. It will never be perfect, of course. And then the next step, designing these kind of charging algorithms that can be really used in practice. There we looked especially in our recent research to a technique from the AI, which is called reinforcement learning, where the goal is in fact that you have an agent that learns by processing data what are the best control actions to take in a certain situation. So in the beginning, the agent is very dumb, and it just takes random actions, and based on the outcome of those actions, if they are good or not good, they get a reward or a penalty. And so over time, they, let's say, learn what a typical charging policy is for a certain environment. So it's pure data driven and has the advantage that you don't need to more manually create models of let's say, distributions of typical arrival times or energy needs, etc. It's all implicitly learned by the agent, which is nice because it's pure data driven. It can be easily be applied to other locations with let's say, other contextual circumstances. Of course, on the other hand, you need to have enough historical data. That's a drawback. But also there, we are investigating how we can, let's say, reuse trained models from a certain location in another location that they don't have to be retrained completely from scratch, but some information from a similar environment can be reused. Yeah, this slide shows on a bit more in detail how the algorithm works and how it then trajectories are learned through the let's say, the overall state space based on the input data, but I won't go too much in detail on this one. And of course, yeah, we did an analysis. Yeah, this approach, can it work? Does it work well compared to, let's say, a very dumb scenario and a business as usual scenario, which is shown here in with the red line, or a very simple heuristic. And then the actual learned policy, the blue line, clearly performs better than this red line, but not as good as the most optimal scenario, which is the green line, where you have a normalized cost of 1, where you know everything on beforehand. But the evaluation shows, okay, this is an interesting approach to further investigate. So we are currently further working on this approach, trying to make it even more optimal and also improve scalability, etc. Another research activity in the energy domain where we also use AI techniques, which can also be interesting for energy communities, more than towards end users, residential end users, is NILM, which stands for non-intrusive load monitoring. So the idea is that you measure the total energy consumption of a household and then try to disaggregate that energy consumption in the consumption profiles of the different appliances in your home. So if you measure that consumption at a high frequency, you can derive, let's say, particular aspects of different appliances that are turned on and off. You can learn that also using data analysis and AI. And of course, the benefit is that you only have one sensor, but still have a lot of information about those different appliances in your home. You can give detailed advice to the end users on how they can improve energy efficiency, what their standby consumption is. You can maybe even find devices that are not working very well anymore, identify anomalies, maybe detect old devices that might be replaced by newer ones that are much more energy efficient. And can easily even learn you something about typical activities and presence of the users in the home, which might be interesting for even very other applications, more in the domain of comfort and security and even healthcare, to, for example, follow up older people at home. But of course, to be useful, it should be able to detect quite accurately which appliances are turned on and off in your house and what the consumption is of those appliances. So we investigated how we could improve that classification accuracy. And the idea we developed can be seen on this slide is that when a power change is detected in your total household consumption, so device is turned on or off, we make a snapshot short snapshot of voltage and current, and then map those on a graph. And based on the electrical characteristics of your device, you will have different graphs, which you can see here on the left, these VI trajectories. And thus, because you have something different here, it's possible to then classify your devices by converting those graphs to bitmaps, and then use a typical neural network to classify images. And as such, you can quite accurately classify these consumption events into the correct consumption events from a certain device. Of course, if electrical characteristics of these devices are very similar, like for example, an electric heater with a hairdryer, the classification is a bit less good, as it's more difficult for the algorithm to detect to classify the correct application. As mentioned, there are also other research teams within IMEC affiliated to energy field that also work on other aspects of relevant aspects in the energy domain, and I'll also briefly present some of their research. Originally, they are still ongoing. They work a lot more on hardware aspects, like improving the efficiency of solar panels is an important research domain, where they have been working on for many years already. One of the tracks they're working on quite right now is improving efficiency from bifacial solar cells, where also reflected solar light is it's also used to generate power. Another domain that they're working on is more on the energy storage, so creating new types of batteries based on solid state lithium ion, which has the promise of a higher energy density, but has still some difficulties to produce on large scale. But you're also working more on software aspects, and one of those things they're working on is they created a very accurate prediction forecasting model for PV panels. From their knowledge on the hardware, they created a physics-based model that can very accurately, on a local scale and on small time scales, predict how much energy the solar panel plant will produce. They also use local cameras to measure or detect clouds in the sky. They also take those aspects into account. And as such, they can very accurately get an idea of how much energy can be expected on a certain location, for example, a local energy community. With such a tool, it sounds good. You can easily simulate on beforehand, before you install PV panels, what the production will be. You can also use it to improve operation and maintenance operations. If production is lower than expected with your model, there might be a problem locally that you should try to solve. And as said, it allows you to do short-term forecasting and can then be linked with a local energy management system to optimize, maybe, for example, also flexible assets, as mentioned before. We're also looking at combining this PV forecasting and monitoring with batteries, which allows you, for example, again, for a community to have a much more smooth profile of local production instead of a fluctuating profile if there are some clouds, or to even deliver ancillary services locally or more globally to the public good. As last part, I would like to mention a few research projects where we are involved that are going on in a few energy communities in Flanders, also where this research is applied. First one is a city district in Antwerp, which is called New South, which is a large project where a lot of apartments are built in different phases. You can see it on the top figure, and it's quite big buildings that are built there. If you drive from East Flanders to Antwerp, and when you come out of the Kennedy tunnel, you can see those buildings at your left side. It's very close to that point of the highway around Antwerp. And there's a research project going on there where we are involved called Circular South, where we try to create a really community with the people living there that is very sustainable, very circular. So we monitor energy, but also waste production, also water consumption of those people. and then give them detailed feedback via an app and give them tips and nudges to try to improve their energy efficiency or to maybe reuse materials more and really change their behavior. We also use blockchain techniques to give them surplus as kind of virtual currency if they do well, which they then can use to buy some city services together with the city of Antwerp. Another new city district that is under construction is a new docks in Ghent, also in different phases, as you can see on this slide. Mainly housing units, over 400, a few offices, but also a city complex, a school with some sports infrastructure here in the middle. This cube is a school with sports infrastructure. Here you can see how it looks like currently. So the first phase in the middle has been finished, and the first people are also living there now, and also the school is already used. And it's the city district has been designed from the start in a very sustainable way, also as a multi-energy district, as other districts have been presented already today, with a heat network where waste heat from a nearby company is reused. But they also process waste, wastewater from the city district, extract heat from that to also be reused for heating the apartments. Also, the processed water is then reused by this company. Some nutrients are recovered from the waste and used for the soil, improve the soil. You also look into mobility, electric bikes, electric vehicles, also electric cars, also sharing of cars, etc. So they try to optimize as much as possible and are also constantly looking for opportunities via research projects to even further improve sustainability of this district. And together with them, we are now involved in 4 research projects where we analyze aspects to further improve, let's say, sustainability of such a local energy community. Yeah, I have to say that also all the inhabitants are part of a local, how we call it, kind of community and company, in fact, but they also have, let's say, shares of all the common energy systems. So all the inhabitants are also motivated in that way. And the first project is the Flux50 Icon project, so a local project called Rolex, where not only in this location, but also in 9 other pilot sites in Flanders, we investigate how local energy communities can be set up, what are the impacts technically, economically, regulatory, but also for the end users. Then there is a large demonstration project, Horizon 2020 project Interconnect, where the focus is more about the interoperability and the communication and the data models to be used to communicate with flexible devices in buildings, in houses, in these kind of districts for energy services. So how can you better connect energy grids with buildings? How can you easier communicate with all kinds of assets from different vendors? And especially SAREF is used there as investigated as data model. Renergetic is a recently started Horizon 2020 project where we focus more on the self-sufficiency of an urban district, so to create a kind of urban energy island. Not that it will be completely disconnected from the public grids, but still try to optimize as much as possible different energy streams in the district, both electricity, heat, but also the processing of the waste, etc. And try to become as much as possible energy efficient and self-sufficient. And finally, Bright is another Horizon 2020 project recently started where we look more at how can we unlock flexibility in those residential areas and those apartments and also the common systems, and use that flexibility on a higher system level, so by aggregators to use that flexibility for services on energy markets and towards the wider energy grid. So that was what I wanted to share with you today. If there are any questions, please.
Thank you, Matthias. A question in the chat: do you consider batteries for electricity or heat in the multi-energy district project that you have presented?
Yes, and this so in Ghent there is indeed also on a community battery. I forgot to mention that that is already installed and used to optimize the local energy production and consumption, and also try to minimize energy costs for the whole district.
And then technology maybe that you use? Lithium?
The exact I think a standard lithium-ion battery. I don't know the exact specifications, but I believe it's a few hundred kilowatt hours power storage, and also the 100-200 kilowatts power charging and discharging rates. But I don't know all the details. I should check that.
All right. Okay. I think it's quite sufficient for the information. Thank you, Matthias, for this clear presentation. As you show the energy in district, the positive district energy are a very hot topic for the Horizon Europe right now. There is a numbers of projects and opportunities over there, so you can be a great partner for the for this type of project. So I invite the different players to contact you if they have projects about multi-vectors energy in a district, for example, and the use of specific technologies in EA. So thank you. We are arriving in the end of this session. So next week we will discover the SMEs front runners, and we will have the presentation of different great players in the market already that have technologies provided in the market. Is SDM, CET, CET, Energrid, Enervalis, NG, IRC, Memoco. So it's small and as well big companies that will be presented next week. And the last session will be in the end of March for the business cases workshop. So the objective will have a discussion between the players in the room about the energy communities business cases that we can create. And in the beginning of the session, we will have a presentation from Delta, consulting company that are already working on the business models in Netherlands and France and Europe. And so she will present a different business model to give some ideas before to go in more workshop and discussion level during the day. So if you have some meetings, you can still take meetings for the B2B meet and match and use the tool from Flux50. Flux50 is providing a match tool, so don't hesitate to use it. And so thank you. I see that there is a question in the chat. So a question for the Living Labs in general. Living Labs are testing new technologies and business models, but could it serve as a lab for the future national, regional, and local regulation? So maybe someone from the speakers can answer to that question more related to the regulations.
Yeah, I can maybe also indicate how we at Energyville tackle this question. As I indicated, indeed, the envisioned strategy for a Living Lab is to answer these kind of questions, to go beyond the current practices, both on technologies, but also at policy level. So that's why we have the advantage of having acknowledgement as a regulatory sandbox, which enables us to move with certain levels of degree of freedom and making aside current practices on regulation and current practices on national policy implementations, and move forward and see if we, regardless of policy, implement certain innovation technologies. How does this provide answers to current challenges, to current practices? Is there societal benefits? And in the end, we want to come up with guidelines, but also position takings for future legislative practices. And we would guide also policymakers in these topics, as for example, the aspect of energy communities is very new, and we see a lot of national and regional governments struggling with implementing a fit regulatory framework for these energy communities. And as you see, the current legislative proposal is really stuck to opening up to these concepts, but however, it's still lacking this kind of facilitating framework to support these kind of energy communities on different levels, like a business case, technology support, etc. So it's via these kind of setups as our regulatory sandbox lab setups, which make abundance or abstract of current practices of legislation. We could really support these governments in implementing these kind of future integration of legislative proposals.
Yes, thank you. And we have a session, the second session was about the regulation of energy communities, and we have seen that even in Belgium we have 3 different ways of translating the regulation from Europe through to the different regulation. We have still a basis that is common, but for the details it's different. And for sure, when we are speaking about the energy communities, it's in the details that is very important. For sure, if we change a small amount in the tariff scheme, you will change a huge part of the business cases. So it's quite complicated, and so that is why we need to speak to each other, and we need these living labs and to speak between the living labs for sure. So thank you for your answer. So if there is no more question left, I close this session for today. I thank you, the different speakers, and I think as well Flux50, it's always a pleasure to work with them. So bye bye, and see you next week for another session with the SME frontrunners. Bye.
Bye, and thank you, Cedric.
With pleasure.